Good morning, all. In the previous class, we have studied about power diode and its related characteristics like operating Chara, transfer Chara, switching Chara, all these things we have seen in detail. So in this particular class, we will study about power MOSFET, the structure, operation, everything. So let's see. So power MOSFET is a type of MOSFET. So MOSFET we have already studied, right? Which is specifically meant to handle high level of power. So our MOSFET, the advantage is it handles high level of power. So MOSFET, I will just expand, even though you have studied already. So it is metal oxide semiconductor. So it's actually a metal oxide semiconductor. When expanded, it is metal oxide semiconductor field effect transistor. Field effect transistor. So that is MOSFET. So power MOSFET means it will be using for high level of power. So metal oxide semiconductor field effect transistor will be used for high level of power. That's why we call it a power MOSFET, just like the power diode. So normal MOSFETs in case of low voltage levels, however, its operating principle is similar. So now let's see the structure. So power MOSFETs are they are N-channel enhancement or P-channel enhancement. So why the name enhancement and all, we'll see in detail. So if you are using N-type material, it will be N-channel, and if you're using a P-type material, it will be a P-channel. Okay, so this is actually the basic structure of N-channel enhancement MOSFET. So we'll see. So in a transistor, you know that there will be an emitter base collector. So transistor, it will be emitter, base, and collector. But in case of a MOSFET, so MOSFET has a gate, source, and drain, right? So emitter base. So the application is same only. Okay, so we'll study the structure in detail. Okay, we will see what is the difference in structure. So the figure actually shows an N substrate VDMOS made of like metal oxide semiconductor made of N substrate and an epitaxial layer. So there is an N plus substrate and an epitaxial layer into which P and N plus regions are embedded. So this is actually the epitaxial layer. So in power diode also you have studied about an epitaxial layer, right? So N plus substrate and then N minus epitaxial layer, and on that we have the P plus 2 P plus, in which P and N plus regions are embedded using double diffusion process. So basically the structure will be on P substrate. On the P substrate, two heavily doped N plus regions will be there, and then the P substrate in turn will be on the epitaxial layer, and then we have the N plus substrate. Then also we have an insulating layer of silicon dioxide, XiO2 is drawn on the surface. So silicon dioxide will be there, is a gate oxide, which will be drawn on the surface, and this insulating layer is embedded with metallic source and drain. So there will be metallic source and drain. I will use another color. So there will be metallic source and drain terminals. Note that N plus region make contact with the source and drain terminals. So N plus region make contact with the source as well as the drain terminal as shown in the figure. I hope it's clear. So this SiO2 there will be metallized so that we can have the source as well as the drain, and they will be contacting the N plus layers. And also a layer of metal is deposited on SiO2 layer so as to form the gate of MOSFET in between. So gate will be there. So now we have the gate, source as well as drain, just like the emitter, base, and collector in a transistor. So I hope the structure is now clear for you. So N substrate, power MOSFET. Now let's see how this is working. So what is the process happening, how current will be flowing when we are giving a positive gate pulse flow. Of course, it's a switch, right? So initially, when the gate circuit is open, so there is no supply coming here. The junction between N plus region, that is gate to source voltage, is 0. Between N plus region, gate circuit is open, junction between N plus region below the drain, so this below the drain, and P substrate is reverse biased. So we have a reverse bias by input voltage VDD. So this input voltage VDD will be reverse biasing the N plus region below the drain P substrate. Therefore, no current flows from drain to source and load. So from the drain to the source, like this current will not flow because VDD actually reverse biases. So VDD reverse biases the N plus region below drain and P substrate. So now when a positive gate pulse is given, when the gate is made positive with respect to the source, an electric field will be established. So this positive is coming here. So this will be positive, and then the other side. So this area, this metallic layer will get polarized. So this metallic layer will get polarized, and this other side will also become negative. So in case polarization, you know, so this will be negative, this will be positive, right? So N-channel planar enhancement MOSFET, N plus region is diffused on P substrate. Right? This N plus region is diffused on the P substrate. So here you can see that always one layer will be reverse biased when source to drain is positive or negative. So whenever the source to drain is positive, always one layer will be reverse biased. When the gate pulse is given, the SiO2 layer will get polarized. This SiO2 layer will get polarized. So negative charge will get induced between the two N plus layers. So you can see that negative charge is getting induced between the two N plus layers, and electrons will pass from source to drain or drain to source, right? So negative charge is getting induced between two N plus layers so that electrons can pass from drain to source and source to drain. So I have given everything, all the notes in detail because this is actually a theory subject. So in order for you to read and understand, I have given all the theory also here. What I'm explaining, I have written here. So you can write down the notes also, and you can listen to me and then write the notes also. So the induced negative charge in the P substrate below gate layer are formed, thus causing the P layer below gate to become an induced N layer. The same thing. So there will be a flow of current from drain to source or gate to source depending upon the polarity. As the gate voltage is increased further, more charge get induced and conductance increases and resistance will be decreasing. So as VGS increases, conductance increases and resistance will be in turn decreasing. So that's what we have written here. These negative charge called the electrons form N minus channel between two N plus regions and N minus channel between the two N plus region, and current can flow from drain to source as shown by the arrow. So the current can flow from drain to source. If VGS is made more positive, induced N channel becomes more deep and therefore more current flows from drain to source. This shows that drain current ID, so this is actually ID, drain current ID is enhanced by the gradual increase of gate voltage. So hence the name enhancement MOSFET. So the drain current ID is getting enhanced. So that's why we call it a enhancement MOSFET. So now you understand why it is called N channel, because we use an N-type material. Then enhancement MOSFET because with the increase of VGS, the conductance is increasing. That is, the gate current ID is getting enhanced. That's why we call enhancement MOSFET. Metal oxide semiconductor field effect transistor. That's the working. So now let's add some more things. Already explained things only. Further, there are wide variety of power MOSFETs like the verticals. That's why VDMOS. VDMOS means vertically diffused MOS or double diffused MOS, DMOS, UMOS. These are types of metal oxide semiconductors. Here the channel is formed in a P-type region. When the gate to source voltage is made positive, that will be a P-channel enhancement MOSFET. Most importantly, here the source S terminal is placed over the drain terminal, forcing a vertical structure. That is why we call it vertically diffuse. The structure also you have seen, right? As a result, in VDMOS, the current flows beneath the gate area vertically between the source and the drain terminals through numerous N plus sources conducting in parallel. That's what you can see here, how the current flows from the drain to the source. So, as a result, the resistance offered by the device during its on state RDS is much lower than in case of normal MOSFET. That's why I told you, when the gate to gate voltage increases, the conductivity increases, that is the drain current increases, that is ID increases, that is ID is getting enhanced. As a result, the resistance is much lower. RDS on is much lower. And the resistance of the device seems to be double as the current increments by about 6%. So more the current, less will be the resistance. And on the other hand, this resistance is actually influenced by the junction temperature TJ. And it seems to be positive in nature. So this actually shows the how can we dependence of RDS, that is the drain to source resistance on current ID. So this actually shows, so more the current, like after a certain point it is increasing. Then the dependence of RDS on junction temperature also you can see, like after some time it is also increasing. So dependence on drain to source voltage on current, as well as the depends on drain to source voltage on the junction temperature. These two things are important. Then, if you observe the structure of MOSFET, you can see that there is an existence of a parasitic BJT. There is a bipolar junction transistor, you know, NPN or PNP, two types. So here you can see there is an NPN parasitic BJT, bipolar junction transistor. A parasitic NPN bipolar junction transistor exists between source and the drain. The P body acts as the base. So the P body will be the base here, base, and N plus layer as the emitter. So this forms the emitter or the source. And so this is actually the source area, right? And N minus layer as the collector or the drain. So this is the collector part. Since the source connected to both base and emitter of the parasitic BJT, the source short circuit both base and emitter. As a result, the potential difference between base and emitter of the parasitic BJT is 0, and therefore BJT is always in the cutoff state. So for a power MOSFET, since the base and emitter short circuit both base and emitter, source actually short circuit both base and emitter, the BJT is always in a cutoff state. Vertical travel from source to drain indicates the existence of a parasitic diode also. You can see there is a PN diode. PN diode, the parasitic diode, with source acting as anode and drain as cathode. So source will be the anode and drain will be the cathode. They can be used as half bridge or full bridge rectifiers in the application. So the parasitic diode also shows that reverse blocking capability of BJT of P-MOSFET is always 0, almost 0. So we have a parasitic BJT and a parasitic diode. So PN and NPN. So you should understand what forms the emitter-based collector here and what forms the anode and cathode here. So this with parasitic BJT and body diode. Now let's see the transfer characteristics and output characteristics. So this basically shows the circuit diagram. So this is actually the basic circuit diagram. So this is the circuit diagram. So you can see that this is the gate voltage. So this is coming here, and this is a simple. So before that, first of all, let me introduce you. Let me teach you the simple of MOSFET. So you know that there is a gate, drain, and source, right? So this is the basic simple. So this is the gate. So we normally you go for the N-channel MOSFET. So this is the gate, this is the drain, and this is the source. So coming to a practical figure, so this will be the gate, this will be the drain, this will be, so this is IR of 540, a particular MOSFET of 33 ampere, and the specifications are given, 100 volt maximum is there. So comparing to that, this will be gate, drain, and source, 1, 2, 3. So now let's see the circuit diagram. So the circuit diagram, so this is the gate, drain, source, and this is the RD, output voltage, and VDD, drain to drain voltage also is there. So the source terminal S is taken as common terminal. So this is the common terminal as usual between the input and output of a MOSFET. So this is the input and this is the output, right? So we can see that for a power MOSFET, the transfer Chara is given here, that is plotted between ID, that is drain current, and gate to source voltage VGS, that is the transfer characteristic, and output characteristics plotted between ID and VDS. So this is the current ID, and with VDS, drain to source voltage, and transfer Chara is plotted between output current ID and gate to source voltage VGS, input voltage. From the figure we can say like that, right? Yes. So an explanation to the transfer Chara will be, so it shows the variation of drain current ID as a function of the gate source voltage VGS. So the threshold voltage VGST, that is the threshold voltage, is an important parameter of the MOSFET. VGST is the minimum positive voltage, or we can even write it as VT. It is the minimum positive voltage between gate and source. So minimum positive voltage between the gate and the source to induce the N channel. Thus, for threshold voltage below VGST, device is in the off state. So this is an off state. So magnitude of VGST is order of 2 to 3 volt. So this can be 2 to 3 volt. So this is the minimum positive voltage between gate and source to induce the N channel. So that is the transfer characteristic. After that, this will increase as shown in the figure. Now coming to the output Chara, which is very important. So output Chara is drawn between ID and drain to source voltage VDS. So output Chara is drawn between ID and drain to source voltage VDS. So here we can see for a given VGS, so gate to source voltage for a given VGS, consider 0 volt. If VDS is increased for a particular value of VGS for 0 volt, VDS is increased, or you can at least consider 1 volt increase, output characteristic is relatively flat, indicating that the drain current is nearly constant. So you can see that here the drain current is nearly constant value because it's a parallel constant value, parallel to x-axis, the y-axis will be a constant. A load line intersects the output characteristic at A and B. So this is the A and B points. A load line intersects A and B. Here A indicates fully on condition and B fully off condition. So this is the output Chara. Here P-MOSFET operates a switch either at A or B, just like the BJT. So let's see, when the power MOSFET is driven with large gate source voltage, MOSFET is turned on. So drain to source on voltage will be very small. VDS on will be very small initially. Here the MOSFET is acting as a closed switch. So it's set to be driven in the ohmic region. When device turns on, P-MOSFET transfers ID VDS characteristic cut off to active region and then to the ohmic region. So you can see here that how the characteristic is changing. So initially it is at it is linearly increasing, and after that it is going as a constant value for a for a particular value of gate to source voltage. So here you can see how the Chara is changing between the ohmic and saturation region. So it will be going from cutoff to active region and then again to the ohmic region. So that's the saturation region and the ohmic region. And this is the maximum value. This will be the breakdown region. That is the drain source breakdown voltage. This is drain source breakdown voltage. So I hope the output Chara is also clear for you. So you should understand the output Chara with the circuit diagram given here. So the three important areas are cutoff region, ohmic region, and the saturation region. So the Chara will be shifting in between these three regions. So I will mark the cutoff region here also. There's very small values given here. So cutoff to active and then to ohmic region. So active is saturation or active region also you can say. Okay, so this is a circuit simple which I have already explained, and this is N-channel MOSFET which you will find in the laboratory. So corresponding figure it is here. And then last and final, we will see the switching waveforms. The switching characteristics of a power MOSFET are influenced to a great extent by the internal capacitance of the device and the internal impedance of the gate circuit. So things which are important here are the internal capacitance and the internal impedance. So let's see. At turn on, there is an initial delay. So during turn on, that is gate to source voltage, there is an initial delay TDN. So we have the gate voltage VG which we are providing, and then we have the gate to source voltage, and then the drain current that is flowing from the drain to source. So during turn on, there is an initial delay TDN during which input capacitance charges to threshold value VGST. So TDN, the capacitance is charged to VGST. Here TDN is called the turn on delay time. So switching Chara, how it is getting switched on, we are explaining. There is a further delay TR called the rise time, during which the gate rises to VGSP. So during the right time, it is getting VGSP. This further delay TR is called the rise time. So VGSP is the voltage sufficient to drive the MOSFET into on state. During TR, drain current rises from 0 to full on current ID. So you can see the drain current is going from 0 to full on current ID up to TR. So what will be T on? T on will be TDN plus TR. That is the turn on delay plus rise time. So the switch is on. The turn on time can be reduced by using low impedance gate drive circuits, gate drive sources. Okay. As MOSFET is a majority carrier device, so you know MOSFET is a majority carrier device, turn off process is initiated soon after removal of gate voltage at time T1. So this is on and then this is working. The voltage, we are getting a constant voltage and ID is also increasing. At time T1, the gate pulse is removed. So the turn off process will start at that particular instant itself, that is the voltage. The turn off delay TDF is a time during which the input capacitance discharges. So this is TDF, the time for the input capacitance to discharge from V1 to a value that is VGSP. That is that voltage which was sufficient to drive the MOSFET. The fall time TF is a time during which input capacitance discharges from VGSP to the threshold voltage. That is VGSP to the threshold voltage. And during TF, drain current falls from ID to 0. That is from ID to 0. So when VGS less than or equal to VGSP, P-MOSFET turns off completely. So below that, the MOSFET is turning off completely. So I hope the switching Chara is also clear for you. That is switching Chara. waveforms. So now let's see some application of the P-MOSFET. Like you should know. So basic thing is it is used for high frequency switching application varying from a few watts to kilowatt for high power. Like 500 volt, 140 ampere rating device, very popular in switched MOS or SMPS and inverters. So these things you will study detail. SMPS and inverters you will study details in the coming classes and in the higher classes also. So 50 volt to 500 ampere. So what is being, so we already explained this. The on resistance of MOSFET increases with voltage rating. This makes the device very lossy at high current application. Since the on resistance have positive temperature coefficient, parallel operation of P-MOSFET is relatively very easy. Parallel operation is very easy. So that's why we can use that in SMPS inverters. And the positive temperature coefficient also reduces the second breakdown voltage effects in P-MOSFETs. So for high frequency, high voltage things. Now let's compare. So because I want to deliver completely what PS Bimbra textbook is offering to you. So let's compare what is the similarity of a P-MOSFET with a BJT. So basic things you should know. So BJT is a bipolar device, whereas P-MOSFET is a unipolar device. So this has two polarity and this P-MOSFET only has a single polarity. And P-MOSFET has high input impedance of the order of mega ohm, whereas BJT, it will be up to kilo ohm only. P-MOSFET has lower switching losses. Switching losses is very less for P-MOSFET, but its own resistance and conduction losses are more. And very important, P-MOSFET is voltage control and BJT is current control. Even though you haven't studied BJT in detail in this particular curriculum, because that's not mentioned in your syllabus, you should understand that P-MOSFET is voltage control. P-MOSFET has positive temperature coefficient, already explained. In P-MOSFET, secondary breakdown does not occur and it has high voltage rating, so have more conduction losses. So available rating up to 500, 140 ampere, whereas BJTs are available with rating up to 1200 to 800 ampere. So we have studied what is P-MOSFET. So power MOSFET and power BJT, so that can be combined to form an IGBT, which you will be studying in the next class. So I hope whatever we have studied today, I will just summarize. So what all things we have seen today, the structure, then how it is working, then transfer Chara, output Chara. So before going to the transfer Chara, the circuit diagram. Before that, one more thing was there, parasitic, BJT and diode, circuit diagram, transfer Chara, output Chara, and then the switching Chara. And then we have the applications. Then power MOSFET versus BJT. So I hope everything is clear for you. Thank you.